So recall that last time we discussed what are irreducible actions, and I also talked about the orbit stabilizer theorem and how any irreducible action of a group on a set is essentially isomorphic to the action of group on set of left cosets of a particular subgroup. And there we chose that subgroup to be stabilizer of a particular element in that set. That is, which was x each to be g of x for some x in x. Yeah, and using orbit stabilizer theorem, we also showed a few applications of like Lagrange's theorem, and also that uh, order of HK is just this, right? So now in this video, I'm going to talk about the class equation of a group, and again we'll see one or two corollaries. So recall that the class equation in general we have this, where xg is the set of all fixed points of the action, and rest of them are just those orbits which have more than one in. So we denoted that with u minus xg. Yeah, and so in particular, if you consider this action of g on itself by conjugation, there you get that the group is the set is g itself, and the fixed point means say stabilizer of any point is just all those elements of the group that commutes with that element. So the set of all fixed points will just be the center of the group. And for the rest of the elements, I can use the orbit stabilizer theorem. So orbit of like, cardinality of orbit of x will then be or order of g mod order of the stabilizer of x. But stabilizer of x is just the centralizer of x in g. So this is your class equation that you all are familiar with. This is the class equation for a group. So now, like in particular, if G is a P group, then a P group means order of G some power of P, where P is a prime. And so now observe that from the class equation we get that P divides the left hand side. And also in the right hand side, if you consider any uh, such order of G by stabilizer or say centralizer of X, remember for these X are those elements of the group which have non-trivial orbit. That is, the orbit must have at least two elements. So in this case, uh, there will be at least one prime divisor, P. So P divides each of them. So P divides the sum, and also P divides the left hand side. So we get P divides the order of the center. So in particular, center has order at least P, and more so center is non-trivial. Yeah. And this is number one. And from number two, if you have a group of order PQ, say non-abelian, then from the last observation, it follows that the possibilities for center is that it's a subgroup of order either P or P square. But if the order is P square, then you get again a contradiction that is easy to see because the index of the center will then be a P. So it implies G is abelian. And that will again imply that G is same as order center of G, but G has cardinality PQ, whereas Z of G has cardinality P square. So it's a clear contradiction. So you get the only possibility is center of G must have order P. But P was a prime. So in particular, if you take the any group of order 8, say for P equal to 2, say for example any non-abelian group, we know two of two of such non-abelian groups. Like you can take D4 and also you can take the quaternion. Uh, so and both of them have order 8, which is 2 cubes. So the center will be uh, exactly of order 2. And you know the center of these groups. D4 has center. Say if we denote R by the element of order 4, then the center will be identity and R square. And Q8, the center of Q8 will just be plus minus 1. Yeah. Okay. So enough of applications of class equation. And so from this class equation, I will deduce the three major theorems due to psi, the first, second, and third. But I will do that in a later video. From now, let's see. Uh, Remember, I also talked about counting formula that I promised that I will show it in this video, which is how to find the number of orbits of a particular action, right? If the group is finite and it's acting on a finite state, it will have a finite number of orbits. That is clear. But how do you know how many orbits are there? For that, we have this result. Uh, so let me write the result first. So, so say you have a finite group acting on a set X, uh, and we denote this X mod tilde by the set of orbits of this action. So you get the cardinality of number of orbits is just 1 by order of G sum over cardinality of these fixed points of with respect to G, and you will run the sum over all elements of G. So this is the result. And you see, this is not very difficult to prove because remember, you are what you are doing, you are just summing over all possible uh, cardinality of xg. But what are these? Each xg is nothing but you can consider these order pair, right? So, and also you can take the gx, which is just the counting of say first component, the group elements, and here in this case, you are counting the second component, the number of x. So if you just sum it over G belongs to G or X belongs to X, the sum of the cardinality of those sets will be the same because in either case you are just summing over all possible such pairs, order pairs. So what do you get? This sum is same as this sum, right? But again, from orbit stabilizer, what you know is this is the order of G by stabilizer of X. Right. Now just take this out, and this is just a routine calculation. And so remember uh, the set X has been partitioned because of the group action. So you can consider, and the set has been partitioned into say R many orbits. So you're considering R from O1 to O2, O1 to OR. Uh, so let's see how we can manage it. So see, firstly you consider all those elements of a particular orbit. Say I'm considering to be OI. Okay, I can do that. And then I'm taking I from 1 to R. Yeah. So then what you get is uh, so oh sorry, I made a blunder. This should be orbit of X. Yeah, because there you have the stabilizer of X. So I beg your pardon. So this will be orbit of X. Right. But but look at this. You are taking elements from a particular orbit, namely ith orbit. And for each such elements in the ith orbit, the cardinality of that orbit is same as the cardinality of OI. That is same because if you take x from OI, then orbit of x is same as OI. So they have must have same cardinality. So what you get is just the cardinality of OI, and you are taking just this. Now again, how many such ones are there? The number of elements of OI. So you get this is there, and you get this. This cancel out, and this is this cancel, and you get your result. So this is what is called the lemma, and it is due to Burns. So this is just a nice application of only group, only I would say orbit stabilization, and this little counting. Yeah, so that is it. And in case if there is only one orbit, if the action is transitive or equivalently irreducible, then you get that what you get is order of G is just this. If G action X is transitive. Okay, so this is the result I want to say. Okay, so that is the Burnside lemma. So from now on, so in this video or in the next video, I will mostly talk about what are called representation, and mainly I will not go in very details about representation. I will just briefly talk about Maschke's theorem and some corollaries of that, and I will try to relate it by whatever I said in the last one or two videos. Because remember, representation is also an action, and whatever I said about group actions, like how they decompose into irreducible sub-actions and the uniqueness part. So I will try to talk about those things with respect to representation. How much different will it get in terms of representation? Or will we get the same results that we got in the last videos? So, yeah. So let's see, let's try to relate them. Uh, so yeah, I will just start with the definition of what is a representation. So let's so this is representation. And remember, we already talk about finite groups. So representation is just nothing but a homomorphism from a group G to set of invertible linear maps of a vector space V. Homomorph. And remember, the group is finite, and V is a we will take vector space over C. So now let's see some examples before going into the theorems. There is always, because this is a homomorphism, so there is always the trivial homomorphism is available. That is, I take any G, and that is, so remember, rho acting on any element G is a map from V to C. That is invertible linear transformation, because rho G is an element of GLV. So this is, you can take the identity, right, for all G. So this is the trivial representation. Trivial. Now, this is just the very basic example that you always have in terms of anything. Ring homomorphism, group homomorphism. There is always there. So it's not very interesting anyway. And now talking about some other examples, I can take say, hmm, okay, let's take this one. Say you take the group to be S3, and you take vector space of dimension 3 over C, which is this GL3 of C. And what you do, you just take any element. that will be a permutation sigma. So that is just the identity matrix with its column being replaced according as sigma acts on 1, 2, or 3. So what does it mean? That, for example, if I take the sigma to be 1, 2, 3, then row of 1, 2, 3 is just the identity matrix with its first column being moved to the second place, second column being moved to the third place, and third column being moved to the first place. So this. This will again be a representation if there is a homomorphism is easy to check. I'm not going to do that here. And okay, let's see another example. Let's see, say, uh, representation from Z2 to, let's see, some one-dimensional representation. Here, this the say dimension of V is called the degree of the representation. Okay. So in the second example, it was a three-dimensional, the degree three representation. So let's see a degree, say one representation. So that is GL 1C, but that is same as C star because we are taking all possible scalar, that is one by one matrices, except the zero because you have to take invertible elements. So let's take this one because it is a two element set. Let's just say its generator is X. So the identity element will have to go to the identity. And you may take this to this. This is also a representation that is very easy to see. And in fact, you can like observe one thing in general that if you take a representation, say one-dimensional representation of any finite group, then what will happen? You take any G, you take any say G, then rho G is then because say order of G is n. Okay, so uh, rho of G to the power n, this is just rho G whole power n. That is just one. That is due to homomorphism. So you get that rho G. Sometimes I will write in suffix because that is very convenient. So rho G is a complex number with its nth power being equal to 1. So what are the possibilities of rho G? This is one C star. So rho G is just an nth root of unity, right? In fact, in the previous example, in the third example, I just showed rho that is just minus 1 is the second root of unity. So and here the group was of order 2. So it matches with that also. Anyway, so this is just a basic observation. So now this is an action because you take any uh, you see this is an action because if you fix any G, then rho G will be a map from V to V. That is invertible. Rho G from V to V is linear transformation is invertible linear. It's an action because you take this map, you take rho G of any V, that will just be rho G of V. Yeah. So, and because this is a homomorphism, so you get this group action. Anyway, so let's just quickly relate how one can relate or how much different it can be compared to the simple group action. So remember in the group action, we started with what are called the G invariant sets. So recall that. I'm just stating it here again. Recall Y a subset of X is G invariant if G dot Y is inside Y, right? And from that we also showed this lemma that if let's see this lemma. If Y is G invariant, so is X minus complex. So here what do we mean by G invariant? Because here the set X has also a vector space structure. It is not just a ordinary set. So you need to take care of that as well. You need to take care of things which will preserve the vector space structure because then otherwise it will be of no means, right? If you don't respect the vector space structure. So yeah, then let's see. So here we define a representation. So here we'll define what are called G invariant subspace because naturally we are talking about vector spaces, so we need to take care of this vector space structures. The definition is again same. Subspace is G invariant means if rho G of this is inside this for some subspace say W of V for all G of course. So there is a G invariant subspace and rho from G to GLV is said to be what is called irreducible if only choices for W is either 0 or the entire or V. So these two are very much compatible from the last two definitions. Uh, okay, so let's see whether it is, let's see by means of example whether its Halpern representation is irreducible or not. So that will clear things up. So we have given three examples. Let's see the first one. What is it? It just says that if you take any element from the group and you act it on row, and row of G will be just the identity matrix. Clearly, it is not irreducible because you have these one-dimensional subspaces which are invariant under this action. Because you are just taking an identity matrix. If you just take identity matrix and take any say basis vector, then that will again be sent to that vector itself. So say the subspace generated by that one vector has to be say the invariant subspace. So and if you are considering irreducible actions, then that one dimensional subspace must be the entire space. So uh, the trivial representation is irreducible if and only the group, if and only the vector space itself is just a one dimensional space. That is pretty much clear. So I'm not writing it. So I'm just let's say call it a remark. So let me just enumerate. This is row one. This is row two. This is okay. I'm not going to write it again. So row one is irreducible if and only V is just C. Okay. What about row two? Let's see. So you take this, and remember this has to hold for all the elements. You need to find one subspace such that rho G of any vector from that subspace will again land inside that subspace, and that should hold for any element that you choose. Okay. So one thing you should notice here that whatever G here in this second example, the and whatever say this so whatever the element that you choose from S3, the sum of the rows and the columns will always remain to be same. That is one, right? Because you were just permuting the columns of our identity matrix. So just again, so if you take any such sigma and if you consider the subspace W, which is the span by E1 plus E2 plus E3, where EI is the standard basis vector, you know what I mean. So this is inside this for all segments, right? And so it's a one dimensional and you add the V three dimensional. So row so row two is not is reduced. And naturally it is reduced. And let me just leave it to you guys to find out what about row three. It is just very easy actually. There's nothing to do. You don't need to take care of the group or whatever the action is in this case. You know why. So I'm not going to spend the time. Um, okay, so these are some examples. And now you also had this lemma in terms of group action. So let's see the corresponding result in this case. So what you have that so in this case, what do you think should happen? If you take any G invariant subspace and if you take the complement of that subspace, clearly that's not going to work because that is not even a subspace, let alone be G invariant. For in from the first case, it is not even a subspace because the zero vector, for example, is not there because this is inside W. So clearly, that is too much to ask for here. So what is the second, like the next best thing that you can hope for in a vector space? Like you can't just take disjoint union, but you can take what I call the direct sum. Right? You can take a direct sum of two subspaces, or what is called the complementary subspace of a subspace. That means, in a linear algebra, you should know, or you must know. Because, uh, let's see, W1 direction of W. Then what does it mean? It means that V is equal to this, and their intersection is just to zero. So that is called the direct sum of W1 and W. And equivalently, any vector can be written uniquely as two elements of the subspace. And the expression is unique. Yeah. Okay. Um, so let's see if we can manage to prove that. So let me just state the result in the beginning. Here, let rho v is a representation of a finite group G, and suppose there exists a G invariant subspace W of V, then there exists another G invariant subspace um, W prime such that V is just direct. So that is the Maschke theorem. You will find this theorem in the book by J.P. Sale, the representation of finite groups, and that is in the first chapter. So yeah, what is the philosophy here? In that case, in usual group action scenario, you just need to take the usual complement, the set complement. But here you cannot take that, as I said. The subspace structure will not be there in the complement. So you need to take two subspaces such that that direct sum gives you the entire vector space that you will start. Okay, so let's see how we can do it. So, so firstly, you have given one subspace of V, that is W. So you can always find another subspace, say U, Like there exists a substance that you always can do. That is you such that V is that you can always do in a linear algebra. Right? In linear algebra case, you can always find a complementary substance. Just you take the basis of W, you extend it to a basis of V, and take those extra element that you are like those extra element. If you take the linear span of those elements, you will get U, and those subspaces will be complementary, and so on so on. So that is always there. But moreover, you need to take care of the G invariant. That is the most important thing. Right? So now, so you have this direct sum decomposition. But so naturally, when you have a direct sum decomposition in linear algebra, what comes for free? Projection maps, right? And so there exists a projection map from V to W. Projection map, right? You always have this map whenever you have a direct sum decomposition. And remember, P acts on if you restrict P on W, it acts as identity. You know that there is a basic definition of projection. And if you just square it, you will get the same thing. Yes, so P square is P. That follows from actually this. Okay, so let's see. And remember, whenever you have a projection, this W is just the image of P. Image of P is W. And kernel of P is U, right? So now again we need to find another direction decomposition with W and W prime. So we need to find two things. One such another projection and one and if you get the projection, secondly you need to take that W should be the image of that projection also and W prime should be the kernel of that projection. And moreover W prime should be invariant under G. We need to take care of these many things. So let's see if we can somehow make another projection map with the given information that we have. So let's just define this map from V to V. While say rho prime of any V is rho G. Remember, this is a invertible map rho G. Compose with P, the P that you, the P that you get here, this and rho G. So take the inverse and just sum it over all elements of the group and divide it by order of the group. Now you may wonder why I choose this particular map. You will soon get to know why, and you will then realize how natural it is to choose such a map. Because so firstly observe that if you take V from say W from W, then because rho G is in because W is invariant, so rho G of W will again be W, and Px is an identity. So P of rho G W is W. Sorry, is rho G W. And then, so from here you get that here it's rho G inverse of rho G of W. From the homomorphism part, you can cancel rho G inverse and rho G and you will get again W. So, first thing you observe that P prime restricted to W is just identity map and W is the image of P. That is number one. So then naturally, firstly you get this. The V is then and okay, you need to find that P is actually a projection. Firstly, you need to find that. So I'm leaving it to you to find that rho P prime square is P prime. That is not very difficult. You can do it. So this is indeed a projection. That is easy. Just some computation. And so then you get this V is the V has a decomposition of image of P prime, which is W, and kernel of P prime. So let me just call what So let me just call W prime to be kernel of P prime. I'm defining W prime. Sorry for that. Yeah. So now the last thing you need to verify is W prime is G invariant. So let's see how we can do. It's very interesting. And you will know why I choose P prime to be this. How beautiful it will be. So take any element from W prime and need to show rho G of S is again inside W prime. That is kernel of P prime. That is P prime. Let's just take uh, let's take some H for all H. I'll tell you why. So you have to show P prime rho H of X is 0. And remember what is the definition of P prime? It is just the average of rho G inverse composite rho G over the elements of the group. Remember this is a finite group, so there it is a finite set. Okay. So now uh, let's see. You take this P prime rho H inverse. What will this be? You can take the rho H inverse inside and multiply rho G inverse. You will get rho GH whole inverse. You take this and you get this. Fine. Now, so G goes to GH. This is your map, and this somehow like you are just summing over the elements of the group G and just take GH. Put it in this way. Define GH to be X. So you get rho X inverse P rho X, and your G is here XH inverse. So the sum is like XG inverse, but that is again same because it is a finite group. So you are summing over some different indices. So you are just changing the indices. So that will not change anything. So that will again be P prime. And now it is clear because what you needed to show. So now if you put X in both sides and take so from here you get P prime rho H is rho H P prime. So you get P prime of rho h of x is rho h P prime of x. But remember x is in kernel of P prime because it is in double prime. So that is 0 and this is 0. So you get rho h of this is inside kernel. So what you get is direction decomposition of V uh, into subspaces where both of them are G invariant. And so from here I can uh, easily state what the Maschke's theorem is. It says that any representation can be uh, broken into or decomposed into irreducible representations. And that can be done easily now with the help of the fact that you can take dimension of V to be finite and just do a induction on this dimension. That you can easily do. I'm not going to state it, so I'm just stopping this video with the main result that I proved here, the Maschke's theorem. So it states that any representation rho from G to GLV can be decomposed into irreducible representation. Into irreducible representation. Or sub-representation you can say. And the proof is just use induction on dimension of V and use the last response. So I'm not going to do it here. Just very easy. And in the next video, I will talk about the uniqueness of the decomposition because remember, in the very second video, I told you that this uniqueness is not there, but it was there in arbitrary group action. So I'll just give a counter example there, or maybe you can think about the counter example, and then I will just move on from there. So that's it.